Okay, homework 11, number 10. So S1 is the unit circle. So all the complex numbers of absolute value 1. Prove it's a group. Well, so you know if you take any point on the unit circle, the complex number z is of the form cosine theta plus I sine theta. Okay? That's what a complex number in the unit circle looks like. So prove it's a group. Well, if you have, let's say that's cosine theta 1 plus sine theta 1, and Z2 is cosine theta 2 plus I sine theta 2. So if you multiply them, so how do you multiply complex numbers? The real part is the product of the real parts minus the product of the imaginary parts. And the imaginary part is cosine theta 1 sine theta 2 plus sine theta 1 cosine theta 2. And then you have to remember the addition formula for the sine and the cosine. We've used it many, many times in this course. This is just the cosine of theta 1 of the angle theta 1 plus theta 2. And this is the sine of the angle theta 1 plus theta 2. So this is some number Z3 that's also in the unit circle. So this set of numbers of complex value, of absolute value 1, closed under multiplication. The multiplicative identity is the number 1, which is cosine 0 plus I sine 0. That's certainly in the unit circle. For one thing, here it is right here. That's the point 1. And what is the inverse? If you have z equal cosine theta plus I sine theta, z inverse is cosine of the angle minus theta plus I times the sine of the angle minus theta. Because when you multiply these two numbers together, z inverse, you get the cosine of theta minus theta plus I sine of theta minus theta. That's cosine 0 plus I sine 0. That's 1. So this set of complex numbers of absolute value 1 is closed under multiplication, contains the number 1, and contains the inverse of each of its elements. So it's a group.
But we didn't have to use the x squared plus y squared equals 1.
Do you have to use it? Well, I didn't use it, so I guess you don't have to.
I mean, weren't we supposed to use that? Like, how did you know to use the z equals cosine theta plus I sine theta?
Well, you're like asking, how do you solve a problem? Well, you...
That is not the same thing at all.
Yeah, I mean, you look for something that works. Now, if you wanted to say this circle S1 is all complex numbers z, where the absolute value of z is equal to 1, and if you know that for any complex numbers, the absolute value of z1 times z2 is the product of the absolute values, then you're almost done, because if z1, z2 are in S1, then the absolute value of z1, z2 is the product of the lengths of the absolute values of these numbers, which is 1 times 1, which is 1. So that means the product is in S1. What about the number 1? Well, the number 1 has absolute value 1. So 1 is in S1. And if the absolute value of z is 1, then the absolute value of 1 over z, which is 1 over the absolute value of z, is 1 over 1, which is 1, which is in S1. So therefore, whenever z is in S1, then 1 over z is in S1. So that's a proof. It's an equally good proof, which doesn't use sines and cosines. It just uses the properties of the absolute value of a complex number. That would be fine also.
This problem is, I thought, was similar to a problem in 1.2, number 2A. You don't have to do the whole problem. I just need to know how to start it, because it's very similar. But in that problem, they use x squared plus y squared equals 1.
Okay. Read that problem.
Okay, let me find it real quick. Hold on.
This was problem 10 in homework 11.
Okay, I'm ready. It says that the unit circle in the complex plane is the set of complex numbers, big T, which equals the set of z, equal to x plus yi, such that x squared plus y squared equals 1.
Yep, okay.
So, right, so that's similar, right? So it's saying to prove that T is a multiplicative group.
It's the same problem.
But here they use the x squared plus y squared equals 1. That's why I don't know, like, what I'm supposed to do with it.
Well, that's another way of saying the absolute value of the complex number is 1. You know, just saying the same thing in 2 different ways.
All right.
Can we do computing right cosets and left cosets? For example, 1.6 number 3
Okay.
and number 5.
So you have to read the problem to me. 1.6 number 3, okay?
Consider the transposition tau 1 equals 2, 3
Yep,
in the symmetric group S3.
okay.
And H equals E tau 1 is a subgroup of S3.
Okay.
Compute the left and right cosets S3/8 and H/S3.
Okay. So S3 has 6 elements: the identity, the 3 cycle 1, 2, 3, sigma squared, which is 1, 3, 2, which is the same as sigma inverse, tau 1, which is 2, 3, tau 2, which is 1, 3, and tau 3, which is 1, 2. So now what do we know? We know that the cardinality of S3 is 6, and the cardinality of H is equal to 2. And so the index of S3, of H in S3, is 6 over 2 is 3. So this is going to be the number of left cosets and also the number of right cosets. So let's try and find the cosets. Let's do the left cosets first. So H is a left coset. It's E times H if you like. This consists of E and tau 1. Okay. What's another left coset? Well, I don't know. Let's take sigma H. Sigma H consists of sigma and sigma tau 1. What is sigma tau 1? Sigma tau 1 is 1, 2, 3, preceded by tau 1, which is 2, 3. So this is the permutation that sends 1 to 2, 2 to 1, and 3 to 1. So this is tau 1. So this is tau 3. So this coset is sigma and tau 3. So I have two elements. Sigma squared H is going to have to be the other two elements. The other two elements are sigma squared and tau 2. So these are the left cosets.
Why are you pairing E sigma and sigma squared with H and not
I just
or tau
make a
3?
random choice. Doesn't matter. I mean, EH is obvious because H is a left coset. So I take E and tau 1. Then what's another left coset? Well, take H and multiply it by something that's not one of these two. I have 4 choices. It makes no difference which one I pick. I pick one. And I'll get another coset with 2 other elements. The 2 other elements that are missing, they have to be the ones in the third coset. I don't have to do anything more than that.
So if you chose a different one, you would still get one of these 3.
These are the cosets, no matter what you choose. Okay? Let's look at the right cosets. Well, all right. Let's say, suppose I choose something different. So you tell me what to choose. Something times H. What should I choose?
Let's choose tau 2.
Okay. So tau 2H is tau 2 times the identity and tau 2 times tau 1. Tau 2 times tau 1, let's see, tau 2 is 1, 3, and tau 1 is 2, 3. So this
Can you move
permutation
the
says,
page up a bit?
what?
Can you move the paper up?
Sorry.
Thank you.
So tau 2 is 1, 3, tau 1 is 2, 3. So this sends 1 to 3, 3 to 1, and 2 to itself. So tau 2, tau 1 is, oh, this can't be right. This sends 1 to 3, 3 to 2, and 2 to 1. So this is sigma squared. So this coset is tau 2 and sigma squared. Well, that's exactly this. It's the same as the coset sigma squared H, right? So tau 2H and sigma squared H, they give me the same thing. So these are the 3 left cosets. All right, is there a question about that?
So you can choose whichever ones you want, but if you get the same thing, then you have to do another one. You can't just
Correct.
have it.
Let me try the right cosets. So I have HE, which is H. So that's E and tau 1. Let me do another one. Give me, what should I put over here? Which permutation? Your choice. Anything you like.
Tau 3.
Okay, H tau 3. So I'm multiplying on the right by tau 3. So I get E tau 3 and tau 1 tau 3. Of course, E tau 3 is just tau 3. What is tau 1 tau 3? That's 2, 3, 1, 2. So this is 1 goes to 3, 1 goes to 2 goes to 3, 3 goes to 2, 2 goes to 1, which is sigma squared. So this is tau 3 and sigma squared. I need a third coset. What should I pick? I've already used tau 1, tau 3, sigma squared. The only choices are tau 2 or sigma. And it doesn't really matter which one I pick. It's going to have to be tau 2 and sigma, because those are the only two elements that are left. And you'll notice the left cosets and the right cosets are not the same. Right here I have sigma squared and tau 2. Here I have sigma squared and tau 3. They're different. The elements in in S3 are rearranged differently in the right cosets and the left cosets. And that's because this subgroup H is not a normal subgroup.
This makes sense now. Thank you.
Okay.
Can we do number 5 as well? Let G be a group
Wait a minute.
and let
One
H
second.
be a subgroup.
Wait. This is what section?
1.6, number 5.
1.6, number 5. So G is a group.
And H
H
is a subgroup of G.
Yep.
So define a relation tilde on G as follows. X is related to Y if X inverse Y is in H. Prove that this is an equivalence relation and that the equivalence classes of the relation are the left cosets of H.
Okay.
So we have to prove that it's reflexive, symmetric, and transitive.
Right.
First.
Okay. So how do you prove it's reflexive?
So
So
X inverse X is E, which is an H.
So every X is related to itself. That's reflexive, right?
Mm-hmm.
What about symmetric?
So we know that X inverse Y is an H.
So if X inverse Y is in H, then every element in H has its inverse in H. So X inverse Y inverse is also in H. But what is X inverse Y inverse? It's Y inverse X, which means Y is related to X. So I should have said if X is related to Y, that means X inverse Y is an X, and we conclude that Y is related to X. So X related to Y implies Y related to X. So that's the symmetric property. Is that okay?
Yes.
Okay. And for transitivity, transitive. So if X is related to Y and Y is related to X, that means that X inverse Y is in H.
You mean Y is related to Z?
And Y inverse Z. Sorry, this should be a Z here. If X is related to Y and Y is related to Z, then X inverse Y is in H and Y inverse Z is in H. And H is a subgroup. So it's closed under multiplication. X inverse Y times Y inverse Z is also in H. But this, the Y and Y inverse cancel. This is the same as X inverse Z is in H. So X is related to Z. So this proves that we have an equivalence relation. This relation is reflexive, symmetric, and transitive. And what is the equivalence class of X? So this is a set of all y in the group such that x inverse y is in H, which is the set of all y in the group. I multiply this by x such that y is in XH, which just means it's the left coset, XH. So the equivalence class of X, everything that is related to X by this relation, is exactly the left coset.
Professor?
All right, is that okay?
Yes, thank you.
Okay,
Hello, Professor?
yeah, go ahead.
You may have already done this. I don't need you to do it, but question 4 in homework 11, it says let f from G to G prime be a homomorphism. Prove that if H prime is a subgroup of G, then F inverse of H prime is a subgroup of G prime. I was just wondering, is that correct? Should it be H prime is a subgroup of G or G prime?
Let me take a look. Which number is that? Number
4A, homework 11, 4A.
Yeah, it should say subgroup of G. Because F inverse of H prime is a subset of G, so it wouldn't make any sense for it to be a subgroup of G prime. Thank you.
Right, F inverse of H prime. So shouldn't H prime belong to G prime, not G?
Yep.
The homework says H prime is a subgroup of G, not G prime. So I just want to
No.
correct
So
that.
there's a typo in both parts of that problem.
Okay,
It
so
should
that's
be
what I
that
was
H
clarifying.
prime is a
It should belong
subgroup
to
of
G
G
prime, right?
prime, and H is and F inverse of H prime is a subgroup of G. Thank you.
Okay, perfect. Thank you.
For parts A and B, right?
Yes.
So there should be no G's in A and B, just G prime.
No. It should read, let F from G to G prime be a homomorphism. Prove that if H prime is a subgroup of G prime, then F inverse of H prime is a subgroup of G.
Oh, so they're swapped.
Yes, in both part A and part B.
I'm not done yet. How's this? I'm not done yet. How's this?
I'm sorry, it's very hard to understand you. Can you speak more loudly, please?
Professor, when you answered number 10 at the beginning of this session, were you addressing only part A?
I was only asked to prove that, I guess, so I can do part B if you like.
Would you please?
Sure.
Thank you.
So,
That was homework 11, yes.
yep. So this is homework 11, number 10B. So we have a function from the real line to the circle given by f of t is cosine t plus I sine t. And to prove this is a homomorphism, so this group is additive and this group is multiplicative. So we must show that f of t1 plus t2 is f of t1 times f of t2. Okay. So what is f of t1 plus t2? this is equal to the cosine of t1 plus t2 plus I times the sine of t1 plus t2. And what is f of t1 times f of t2? That is the cosine of t1 plus I times the sine of t1 times the cosine of t2 plus I times the sine of t2. When I multiply, I get cosine t1 cosine t2 minus I sine t1 sine t2 minus sine t1 sine t2 plus I times cosine t1 sine t2 plus sine t2 cosine t1. And by the addition formulas for the sine and the cosine, this is the cosine of t1 plus t2 plus I times the sine of t1 plus t2, which is exactly f of t1 plus t2. So once again, we use the addition formulae for the trigonometric functions.
Thank you.
What else?
How can we prove that if H is a subgroup of Z, then there is a unique non-negative integer m such as H equals mz? And that it's unique.
Yep. Okay.
This is number 6 and 1.6.
So the proof goes back to when we were doing elementary number theory, and we proved the following theorem that says that let H be a non-empty set of integers that is closed under subtraction. There is a unique non-negative integer m such that H equals mz. So corollary of this is exactly this problem. If H is a subgroup of Z, we know it's not empty because it has to contain 0. It's closed under addition and subtraction. So then H equals mz for some unique integer m greater than or equal to 0. The uniqueness, by the way, is easy to prove. So suppose we have mz and nz equal, where m is greater than or equal to 0 and n is greater than or equal to 0. So let's call this set H. So this says that every integer in H is divisible by m. And this says that every integer in H is divisible by n. So m is in here and n is in here, so m divides n, and n divides m. So this says that n divides m means n is d times q. And n divides m means m is some d times q prime. Sorry, m divides n is m times q, and n divides n means m is n times q, which means plug this in here. This is m, q, q prime. So the m's cancel, q, q prime equals 1. So q equals q prime equals plus or minus 1. The only way you can factor 1 is 1 times 1 or 1 minus 1. But these numbers are non-negative. So q and q prime equals 1. So m equals n. I mean, that's the proof of uniqueness. But it's this theorem from elementary number theory that tells us that every subgroup of the integers is the set of all multiples of some non-negative integer.
So we were looking at cases where we would have like, let's say we had 2z, and then a subgroup of that would be 4z. And so that's not a unique number there.
Well, wait, no. For the subgroup 2z, the unique number is 2. For the subgroup 4z, the unique number is 4. It says that every subgroup is the set of multiples of some non-negative integer. So 2z is a subgroup, and 4z is a different subgroup, right? Different
Okay.
subgroups are associated with different non-negative integers m.
Professor, would you mind doing number 9 from homework 11 as well?
I'll take a look. Homework 11, number 9.
Yes, please.
Oh. So we have the absolute value function from the non-zero complex numbers to the positive real numbers, where the absolute value of x plus yi is the square root of x squared plus y squared. So, or the absolute value of x plus yi squared is x squared plus y squared. That's the same thing. So suppose we take two complex numbers. Let's say z1 is x1 plus y1i, and z2 is x2 plus y2i. So we want to show that the absolute value of z1, z2 is the absolute value of z1 times the absolute value of z2, right? Which is the same as saying that the squares are equal. Just take the square root. So this is z1 and this is z2. What is the product? It's x1, x2 minus y1, y2 plus I times x1, y2 plus x2, y1. That's z1, z2. So what's the absolute value of z1, z2 squared? It's this squared plus this squared. So you square it, you get x1 squared, x2 squared minus 2x1, x2, y1, y2 plus y1 squared times y2 squared. And here I get x1 squared y2 squared plus 2x1 x2 y1 y2 plus x2 squared y1 squared. And of course, you can notice that minus this and plus this cancel. So what I have is these four terms. So if I take these two terms, that's x1 squared, and I can factor out x1 squared from both of these, x2 squared plus y2 squared. And from these two terms, I could factor out a y1 squared. And from this, I can factor this out. I get x1 squared plus y1 squared times x2 squared plus y2 squared. And this is exactly the absolute value of z1 squared times the absolute value of z2 squared. So that's just a little bit of high school algebra.
Thank you.
Yep. Other questions I can try to do?
Professor, for question 5 in homework 11, I can read the question if you would like.
No, I have it. That's fine.
Sorry, you have it?
Yes.
So just had a question. So to prove that f inverse of h prime is the kernel, can we basically for the proof, can we just say that, let's say you have f of x where x belongs to g, f of x times h prime is h prime, that means f of x is h prime or belongs to h prime.
That sounds right.
So no, question is f of x h prime or f of x belongs to h prime? That should be the conclusion, right? Belongs to h prime.
Which part of problem 5 are you looking at?
I'm looking at part B, which says that prove that kernel of f is a subgroup of h, which is same as f inverse of h prime. So for my proof, I am basically saying that, let's take x where x belongs to g, such that capital F of x is equal to h prime. And that means that, f of x multiplied by h prime is same as h prime. And my conclusion should be what? That f of x belongs to h prime or f of x is H prime. I think it should be belong to, but I'm not 100% sure.
Well, so let's look at this problem.
Mhm.
We have G goes to G prime by this homomorphism F. And we have H prime is a normal subgroup of G prime. So you have the quotient group G prime mod H prime, and this canonical homomorphism pi from G prime to G prime H prime. And if you look at the composite of these two things, we can call that F. So F of an element X in G is equal to pi F of X. So that F of X is in G prime. So this is the coset F of X H prime.
Right,
That's what capital F of X is.
right,
And X is in the kernel of F if and only if capital F of X is equal to the identity down here, which is the coset H prime, which is the same as saying F of X H prime equals H prime,
right.
which is the same as saying the little element little f of X is in H prime,
Okay.
which is the same as saying X is in the inverse image of H prime.
No, okay. I mean that's all. I was just I just wanted to clarify the second last step, which little f of X belongs to H prime. I wasn't sure
Yep.
whether it's equal or belongs to, but
Well, first, little
it's
f of
clear
X is an element in a group. It's not a
All right.
subset of a group.
now. Understood now. So
So that has to be
clear now.
consistent.
Yes. No, it's clear now. Thank you. Same question, part C. It says left cosets of G and H, left cosets of H in G and left cosets of H prime in G prime. What is that symbol? I forgot.
Isomorphic.
Isomorphic. Okay. So to prove that, we have to basically show that we have to show one example of an isomorphic function.
No. So we have this function from G into this, and we're told that F is onto, and we know that pi is onto. So F from G to G prime mod H prime is onto.
Right.
So the first isomorphism theorem says that G modulo the kernel of F is isomorphic to G prime mod H prime. And we already proved the kernel of F is F inverse of H prime, or H. So H is what we called F inverse of H prime. So G mod H is isomorphic to G prime mod H prime. This is an application.
I haven't looked at the last two lectures, so that's why I don't know that, but I'll take a look at it now. So does that actually mean that if you take the left cosets of kernel of F, basically that function becomes one-to-one as well, because you're removing all the elements that would map to identity on the other side into one set?
Well, I'm not sure. I don't understand what you're asking. If you take the left cosets of H,
Right.
they map one-to-one onto the left cosets of H prime. That's what it means to be an isomorphism.
Right, but F is not expected to be isomorphic. F is just expected to be homomorphic and
No, F is an
and onto.
isomorphism. sorry, F is not F is a homomorphism that is onto.
Right. So
And G modulo the kernel of F is an isomorphism. So you have this function. So if you take G modulo H, H is F inverse, H is the kernel, then you have a function F tilde from here to here, which is an isomorphism.
right. Professor, will you be posting a sort of a review sheet for the exam, or is it basically pretty much the last few homeworks?
It's probably pretty much the homework since the last exam and the material that was covered in the lectures. And I'll think about tonight whether I can put together a review sheet.
Okay. Thank you.
Yep. Okay. If there's nothing else, I will be back tomorrow morning at 11 o'clock. See you then.
Professor, one last question actually.
Go ahead.
So are there any more lectures, or all the lectures are already on the YouTube now?
Everything is on the YouTube.
So as far as the course
I think
concerned,
when
there's
it
no
goes
more
up to lecture 20.
up to lecture 20. Understood. Thank you.